So thank you everybody for joining today's session. It's a pleasure for us to moderate this workshop that will introduce you to the brain tumor segmentation challenge and will serve as an introduction to creating an AI model for medical image segmentation. What is image segmentation? It's the process of classifying each pixel on a 2D image or voxel on a 3D image, as is the MRI you see on your screen, into a predefined category. For example, enhancing tumor marked here with yellow, necrotic core of the tumor marked here with red, edema marked here with green, or resection cavity marked here with light blue. Right now, we are working on the BraTS 2025 challenge. We have already created a reference standard dataset that also establishes intra and inter-rater variability in the ground truth. Just in case you're not acquainted with this term, ground truth is the reference mask that tells your segmentation model what the right answer is for each voxel. But why is it important to have a consistent ground truth? Because the model learns what you teach it. And what is our vision for the future? Our vision for the future is to create an imaging consortium comprising pre and post-treatment MRI cases of brain metastases with accompanying ground truth annotations. To read more about the challenge, please refer to the analysis preprint that is out on arXiv. You can scan the QR code and it will send you right uh, to the link of this paper. So we already had the first event from the workshop series in January, where Amika Multiple Challenges winner went over some of the basics of creating an image segmentation model and also discussed some caveats for what makes a model stand out. So please do check our YouTube channel to find the recording and get acquainted with his talk. If the talk feels too overwhelming, you can reach out to us so that we can provide you with a dumbed down and easier to digest version of his presentation. So the first thing that we need to start doing anything related to creating an image segmentation model is the Python. Just go to the official Python page and download the latest release. So on top of that, it's advisable to run some commands in the PowerShell application on your Windows machine to ensure that your shell will pick up the right interpreter when you run scripts or launch Jupyter. Um, why do you need that? It's just, as I said, a sanity check. One question might arise here, and that is if installing Python and opening PowerShell is enough to run Python code. Well, the answer is yes, but Visual Studio Code, which is a software that my colleague will present in the next couple of minutes, the VS Code makes it easier to write, debug, and visualize code, especially with projects like medical image segmentation that involve multiple files and datasets. So it just makes your life easier using Virtual Studio Code. If you're like me and you have wondered what software do I need to start running Python code on my machine, maybe you have discovered plenty of options. And one of them is Anaconda or its minimalistic counterpart, namely Miniconda. So do you actually need those to be productive and create a medical image segmentation model? Well, you don't necessarily need those, but there's some benefits of using them. You have a massive amounts of libraries that are already installed, like Matplotlib. Matplotlib is a library that allows you to compare ground truth masks with model predictions side by side. And on top of that, Anaconda and its counterpart Miniconda is considered to have a smaller chance of your installs crashing. So you gotta check it out for yourself and find the best solution for you. Here we are. this is the Visual Studio Code. It's considered the go-to software for building many human segmentation models. You can directly open Python notebooks with VS Code, create plots, visualize data, and basically you can unleash your creativity. VS Code also runs on Mac and Linux, so this is why um, it is considered to be the go-to resource. And here is an example of Google Colab. It's a free cloud-hosted Jupyter Notebook service provided by Google. You don't need to install anything, just open a browser, log in into your Google account or your GitHub account, and that's it. You can directly start typing Python code, which is which is why it's so convenient to use. You can also mount your Google Drive if you want to use files that are stored there, or if you want your drive to serve as a temporary directory, or the directory where the training model is saved. So yeah, it's a pretty good alternative. Think about Colab is that you can also set a temporary folder on your local computer or in your drive. The screenshots demonstrate the code that will do the job for you. And uh, yeah, that's it for Google Colab. And from here on, I will welcome my colleague Fabian to continue the talk and provide you with more guidance on the computational side of things.
Both doctors and both engineers or data scientists to actually get involved into medical imaging. And the part I think even makes it makes it more solidified is, as a doctor, once you're able to even build any model from scratch and you see that it's your model and it's working, it gives you some kind of confidence to actually know that this tool that you're actually working with, you at least understand some part, even not all, some foundational part of how it works. And that start building your confidence. So I think the BraTS challenge and what we'll be going through today is just to help everybody get acquainted with what's necessary and then giving us like a fair ground to actually pick up from and learn. So bulk of our presentation will be done on Colab, but I just thought of mentioning VS Code, which is kind of the local aspect of when you want to run or build any AI algorithm. And then GPUs, custom GPUs, so that you can actually build your model and you won't have anything to worry about privacy. That's why it's also good that we share this point. But bulk of our stuff will be done on Colab, since we know the BraTS challenge is like an open source and a public data challenge. So I think first of all, once we have our Python installed, we have our VS Code working, the first step, I know for experts, I don't know if there are any experts here, but it's important that we also mention this. The first step is for you to have a folder where you want to work, where you want to actually build a project in. So just like an example, I would just show, it's just as simple as doing something like this, creating your folder, and then actually accessing it through VS Code. So once everything is set up, you can actually go to where your folder is located, and then you select, and then you click run. And that's kind of like the first step. The next steps here will just be you creating a virtual environment. So a virtual environment is just kind of a separate workspace where you can actually install all the libraries that will help your algorithm or whatever model you are building to work perfectly. Why it's actually a virtual environment is so that when you are building stuff, it doesn't contradict, the libraries in your system doesn't contradict with the ones that your system, that came with your system or that have been the base root of your own system. So you just create a separate space for you to now do all stuff relating to your libraries without having to affect what already works in your system. And it's just like a simple command, you write python-m, venv, and then it automatically creates it. Don't worry, I'm not going to bore you. This is not about what we are going to do, but I just thought of mentioning it so that everybody gets kind of more ease with the process, especially for doctors already. Yeah. So Python already, like, it creates this folder for you. And before you start your project, you just have to make sure that this virtual environment is activated for you to then start working. And if you could check, it's actually different for different kind of system. If you're using a Linux, it's a different command. If you're using a Mac, it's a different, and currently you're using a Windows, you just have to type VNV scripts, then you activate your environment. And when you see something like this appearing on your screen, then you know that you're good to go. So the next step will just involve creating your IPython notebook and then selecting a particular kernel. Let me just do it quickly before going to collab. We'll be doing most of our stuff. Okay. So once you've created your notebook, which is actually useful, why notebook is useful to actual Python files, it helps you to actually debug your code easily. So you can easily catch any problem in your code. But meanwhile, if it's a Python script, you have to run it, then execute and show you which part of your code is actually faulty. So you also need to select a kernel, which for our case is a Python kernel. A kernel is just to help you run a particular type of program. So it can be Python, it can be whatever else, but our case we're using Python. So that for every cell, every code that we run is going to actually interpret that code as a Python instruction. So once you set this up, I think you're already good to go. And yeah, everything works fine. So I think this is just like the first step for everybody to get used to, and then hit the ground running. Next, I'll be going into kind of what we really prepared for this workshop. So for the BraTS challenge, you'll be working with like very massive amount of data sets. Like if you attended the meeting yesterday, you heard that the data set is up to 35 gigabytes, which is very large, to be honest, in my opinion. And there's no kind of penalty for using Colab, which is because the whole competition is based on a public data set. But if you are doing something more in-house, you won't actually be needing Colab. You should be using something more internal, which is kind of your VS Code, which is why exactly we started from there. So I've already drawn this step, so we don't actually have to waste much time. But what I'll be going deep is just explaining some of the concepts that we need to have as an idea when working with this script. And yeah, just for assurance ahead of time, we'll be providing this script, and this script will help anybody. Once you run it, it will help you to actually build a model, even though not the best, but it actually help you build something that actually works, which is actually facilitated by, I don't know if you guys have heard of Monai. So it's spelled MONAI. It's kind of a library built by and managed by NVIDIA for medical imaging. So it's done a lot of the heavy lifting that we're going to be explaining today. So the first step for us is when we've got our data set, which is our BRAT data set, a sample data set actually, and it's organized in a very set format. Why I'm mentioning this data set is actually important that we understand how our data set is structured, because that's what helps you to actually manage the building process. If you don't understand how the data set is managed, it becomes difficult writing your code or making modifications to actually work with this data set. And the whole Monai infrastructure, actually, I think the heart of it, one important part of it will be the input. That's why it actually appears first. So the input has to do with how is your data set structured. So if I'm a person, like a participant going into the BRATS competition, the first thing I would want to know is, after downloading the data set for the BRATS challenge, I want to know how does the data set look like. So for this test case that we're doing, each data set will have a name, as you've seen, BraTS-METS 0001, and within it will now be all the different files for that particular patient ID of that particular case. So you might see different sequences. You might see, let me expand this. You might see things like the T1C, T1N, T2F, T.
Fabian, hey Fabian, you got yourself muted for some
Okay, I
reason.
hope not all the time. I hope all the time I'll be talking that you guys are hearing me.
Yeah, of course. You just
Oh,
did
you're
it like
muted.
2 seconds ago. Yeah, you just did it 2 seconds ago. So no worries.
Okay,
Everything
sorry.
was heard, just the last sentence was not.
All right,
By
thanks.
the way,
Okay.
I'll use the time, the interruption to ask you, how did you add all these cases in Colab? How do you, what did you do to have them here on the left-hand side of the screen?
Okay. Normally once you open Collab, you have kind of a workspace that have already been created for you. And then what you then have to do, if you're actually working with, let's say, Google Drive, and you want to bring your data set via Google Drive, it's a different case. But for my own case, since I'm working with kind of very small data set, I zipped the data set and then uploaded it here. So once I click on this upload, takes me to where I'm storing my data, which is this BraTS. Then I just call it in and it comes in. This particular first line of code is just trying to unzip this code and then get this actual folder that contains what we need. I hope it answers the question.
Yeah. So in 2 words, if the data set is super small, you can directly upload it to Colab.
Mhm.
But if it's really the large data set, you would prefer to mount your Google Drive and import it from there.
Yeah.
Okay, clear.
Okay. So yeah, we've covered how this data. You need to understand how your data set is structured, which will now help you to now build kind of a JSON file or a metadata that will then tell Monai that, oh, we have our data set, but this is exactly how you should know that they are structured. And we have kind of an example code that we wrote for you to, if the data set falls in within this category, you can actually run this code, and it helps create that data metadata for you. But if it doesn't, it still doesn't matter. I'm sure that it's going to fall within something of this nature, and you can actually tweak the code to work to your use case. So an example of it is this. The metadata JSON. So we just simply pass the actual folder containing the data, and then we create two different outputs. We want to be using some for training. I want to be using some for validation. For context, we have just 20 data sets. So we wanted to use 16 for training and then 4 for test. So the whole code is just going to go through the individual folders we have and then extract the images, store them as this part of as image, identifier image, and then the labels, which end with -seg, is going to identify each of them and then store them as label. Then automatically, we want to actually be assigning our different data into tests or into training or validation. And that's exactly what we are doing there. So if of all the whole folds, we're also creating folds. Each files, we actually attach a fold to it. For each files that we wrote the structure, we want to attach a particular fold to it. The essence of this fold, if you've not seen it before, but the essence of this fold is when you're doing your validation, you must have heard of k-fold cross-validation, is for you to use a portion of your data set to do the test before actually testing it on the real test set. So the only way you can actually know which data set to use for this test is when you already pre-categorized some of the data set as a fold or a validation data set. In machine learning, it's quite different because you're dealing with tabular structures. You can use the index to then separate them. But when you're working with unstructured data as we have, you have to actually assign it to make it more logical and more structured. So that's exactly what this fold is trying to do. So every data set here has been assigned into 4 different folds. So if we have 20 data sets, we have 5 data sets per fold. The next step I also want to explain is just basically some people after working with or
Hey,
after
Fabian,
making, yes,
do you mind if I interrupt you for a second?
okay,
Do you mind just when you were explaining on the previous section, I couldn't get like I got the last part with the folds, and the last part of this code actually assigns the files to folds, but the initial part of the code, would you please go through it once again? No, the data organization, for how you structure the data in a JSON file.
okay. Yeah, I think the method we use in doing this is, first of all, we wanted to first of all get the base directory which the data set is stored. For our case, it's stored in this directory called BraTS. And then we now want to create two different outputs or places we want to actually categorize our data, lists we want to store our data in, or our data names in. So since for our own case, we just want to do a training and a validation set, want to separate our data set into training and validation, we then create those two different outputs or two different lists. If we want to do a test case with this also, we just simply do a comma and then add test case, um, just as we have. Then we also need to understand, that's what I'm also going back to, we also need to understand how our data set is. Every data set should actually be organized in exactly the same format, all the digits being like this, and then a dash before the actual sequence. So with that, we know all the sequence existing in our data set, and we just store it as a list. And then we know the number of folds we want to actually categorize our data in. Standard will be 5. This one is just trying to check if there's a CUDA available, which is a GPU available. If not, it's going to actually run with your CPU. So the first case is, when we go into this BRATS challenge, we want to access all the different directories within this BRATS challenge. So what it means, we want to access all the different directories, this one, this one, this one. And within each directory, we also want to do something. So we want to go through each directory. For instance, if you're in the first case, we want to go through all the files and get their directory name. So that's exactly what this part is doing. It's going to get the directory name. And after getting the directory name, it's going to now attach modalities to it. It's going to attach the different modalities to it. Oh, sorry, it's going to use it's going to use the directory name and then attach the different modalities to it with a dash. Since we already know that everything here will virtually be the same, the only thing that will be changing is after the dash. So we might as well just recreate it by ourselves from the ground up. We have the directory name, we just attach dash, and then we'll attach the modality name to that particular case, and then we store it. We do the same thing for the label, but for the label, we don't need to do the modality. We know that it all ends with SEG, and we then attach it. The next part is, after you've artificially created this, you also want to test that it exists, so that you do a sanity check that, okay, this folder that I've created artificially, does it really exist in my system? And that's what this next part is trying to do. So if there are any case that is actually not matching, or the naming structure doesn't follow, it's going to actually skip that case and show you this particular directory where that error is coming from. This fold is, if you're conversant with modulo, so kind of when you do a division, you get the remainder of that division. It's kind of a very, very used logic in programming generally. So it helps you to assign a particular range of values. So for instance, the number of folds that we want to have is 5, and our I can be anything to 20 because we want to look through all the different directories here. So let's just take the worst case, 20. When we are in 20, we want to do 20 divided by number of fold 5. What's the remainder? 0. So we automatically assign the 20th element or the 20th data to fold 0. Yeah, we assign it to, is it? We assign it to fold, let me see, let me show. So yeah, I think we assign it to fold. We assign it to fold 0, I think. Or 20 divided by 5 will be 0. So, but what we are then trying to do was, we now pick all the ones that, why the structure is not, the last element is not actually the fold 0 is because we've already separated it into validation and test. So we can't really know which it did. So we are picking all the fourth fold, and then assigning all those fourth fold into our validation list. And everything that is not the fourth fold, we're just picking it as our training. So definitely, it might be the first, it might be the last, but I don't know. It's definitely of fold 0, our 20th element. When you do 20 divided by 5, the remainder is going to be what that fold number will be. Nicola, I hope it's okay.
Oh yeah, it was Yeah, it was great that we went line by line to understand how we actually structure the data using Python. So from what I understand,
Yeah,
I can utilize this code, but understanding how data is structured and being able to um, structure your data in a JSON file is crucial for uh, any it's crucial for you trying to build a model. Like this is like the uh, the this is the cornerstone of doing an image segmentation model, to understand how the data is structured and how you have to structure your data.
yeah.
Okay, great.
So I think like a sense check that people usually do is after getting the data set in, they actually want to visualize the data set to be sure that it's actually what they're expecting. And this code just kind of offers that avenue for you to be able to visualize your data set in different kind of views, which we've already explained here briefly. The Z, Y, and then X, which are the different kind of planes you want to actually visualize your data. So depending on which plane you want to visualize it, you can either put 0, 1, or 2, where 0 will be your axial plane, 1 will be your coronal plane, which is the front and back view, and then the last one, which is 2, will then be your sagittal plane. And depending on where you want to view, or particularly where the tumor is, you want to get the middle view. So that's why we're actually dividing it by 2. And for our case, we're just doing the coronal plane, which is the front and back view, since our tumor was contained there. And it just gives us kind of an assurance that we actually have, our structure is actually good, or is actually working as we expect. And as Nikolai mentioned, matplotlib also help us to actually visualize the data set as we go. So without further ado, going deep into Monai, there are some documentations. I mean, Monai is kind of a rich community. And I've never seen people done so much documentation and so much notebooks to actually help bring people up to speed with what they are doing. So what we actually got here is actually from the Hello World, I think. Yeah, Auto 3D Seg Hello World, but then we modified it to make it match our case, such as in their case, they don't really create like a template for you to be able to create your file structure. But with this notebook, which we'll be sharing at the end, will help you with that idea or give you a context for you to now adapt it to your own use case. So the first thing you want to provide is your data roots. What's the root data set? What directory do you want to be storing your model and all the files in, which is exactly what we have. You also need something they call an input configuration, as Monai will put it. It's kind of giving the algorithm or the whole system an idea of what type of case or use case are you building this model for. So the kind of modality matters. For our case, we are using MRI, but for other cases, it might not be MRI, it might be CT scan. And you just simply change your MRI to CT so you understand. You also need to supply it with what we call the data list, which is very important, which is exactly what we've already found, our metadata.json. It's just to give him an understanding of how our data set is structured. Then you can specify the number of folds you want to do. What the number of folds mean is after training your algorithm, you want to specify how many how many times it's going to run this validation to check the actual performance of this model. So just as we have 4 different or 5 different folds, if we specify a number of folds to be 3, it's going to use, for instance, fold 1 as your validation and 2 to 5 or 2 to 4 as your test, as your training, sorry. Then it goes to, let's say, fold 2 and use 1, 3, and 4 as your training. Then use 2 as your testing, depending on how it goes. Another important part is the class name. You need to also supply the model of an understanding of what type of use case are you building this algorithm for. Are you building it to be able to segment the whole tumor? Are you building it to segment the enhancing tumor or just the tumor core? So depending, but as you are also getting your data set, it's also important that you understand the labeling of your data. So the labeling I mean is what are the values? What values does each voxel value represent? So one can be just the brain, just the fluid, just without anything concerning the tumor, just the foreground they call it, or background. And two might be your tumor or enhancing tumor, and three might be something different. But you need to actually have an understanding of what each value represents in your data set so that it helps you to now train your algorithm for the right purpose. So, but for our case, we have 1, 2, 3, it comprises the whole tumor, and then just index 1 and index 3, or you can call it label 1 and label and voxel label 1 and voxel label 3 represent your tumor core, and then just 3 your enhancing tumor. You can also supply some additional set, which is kind of the sigmoid, and we've explained what it's useful for. I think it's actually useful when you have multi-class label. You also have a learning rate, which just tells your algorithm at what pace it learns. So a high one might have its own consequences, and a low one might have its own consequences, such as slower time to actually understand the data better. And we also have batch size. This is actually useful so that you tend to make most of your time and also your resources. So depending on how many gigabytes of GPU you have, you can adjust your batch size to work with that. So batch size tells us like how many image are you going to pass into your GPU at once to then process. Yeah, the number of patches per image is just the number of voxels, or yeah, number of voxels per particular image. So I think Monai also have some custom algorithms that have already been pre-built into them, which is this algorithm template. You have the DINTS, the segresnet, segresnet 2D, and the SWI UNETAL. These algorithms are kind of good, but they are meant to act as a baseline for us to then understand, or if it's actually okay for our case, we just stop at that. But for the competition, you actually need to just treat this basically as a baseline model for you to then build upon. So you need to supply, let's say, a particular algorithm that you want to use. If you want to use the 4 of them, you just simply expand your list and you impute the names of the rest. And you then understand that, okay, I'm going to train or do a training based on these different algorithms I have, these algorithm templates I have. You can also supply your training parameters. And at the end of the day, you just pass all those inputs into what we call autorunner. Autorunner is now kind of the engine that then processes all this information to then pass it to the core of the engine to run. So you actually have to initialize this class called autorunner. For our case, we initialize it as runner, and then you can set your training parameters, the number of folds, and when you just come here and call runner.run, it then trains your algorithm and stores the result for you. So just like for our case, I just did only one epoch and everything so that everything runs quickly and we can actually go into the result and explain what's happening. So I supplied only segresnet for this to run. So what it automatically does is it went to our folder, which we gave him. We want to actually store what we are creating in this folder, which is exactly what it did. It first of all download all the algorithm templates that it has into our laptop. And then, yeah, these are the different algorithm templates, but in all these algorithms, we only ask it to say to train a model based on one, which is the segresnet. So within the segresnet, you then start seeing all the different files that went into building these algorithms, such as the config, what are the hyperparameters used, then the scripts that we actually used in actually training this file. One important thing I wanted to mention is maybe some of you might have it at the back of your mind, like if we are just sharing things about Auto 3D Seg, Monai Auto 3D Seg, won't everybody have the same algorithm? That's a good question to ask for anybody that's actually thinking of such. I think Monai also offers 2 opportunities, which is kind of where I'll be picking up from quickly before time. So it offers two opportunities for us to be able to actually improve our model. One of the one is through hyperparameters optimization, and it's kind of almost one line of code you write. So you just need to write runner.set NNI, and you put your learning rate. It only allows for learning rate, unfortunately. So you can test different kind of learning rates that you want to test your algorithm on, and it automatically handles the rest for you. Some people might have the idea to actually build their own particular model that does things the way they want or understand the particular use case better. Monai also offers that opportunity. What it's just asking you to do at the end of the day is, let me see. So yeah, they say users can specify a local folder with algorithm templates and run autorunner. So what he expects you to do, first of all, is to come to this place. You might want to study the different algorithm templates, but you have to make sure that your file is structured in the same format for you to then use it. So let me just quickly show. For you to just use it, you just need to supply the algorithm name, which is essentially the folder name, segres.net. You just supply the algorithm name, and then you supply a path to the algorithm template within your working directory. You just apply a path to that template. So I think an important thing to talk about is layout. Why is this important? I've been trying to actually, like since yesterday to today, I've been trying to actually build like a custom algorithm so that we can actually have something that satisfies the question of people that want to do something more custom and not automated. Um, all in all, I've gotten to the base root of having this layout as the best layout because one, with this layout structure, it helps you to actually work or build your algorithm template for Monai to pick it up from. And also, if you're building any other kind of application, like say you want to build an application on Monai that you're going to render, let's say on cloud or something, he also expects you to build it in this exact format. So you want to have your config file, which will contain your hyperparameters, as we've already viewed here. So each algorithm it creates will also have a hyperparameters telling him or telling Monai the different specification of what you are building, such as the class index. It also tells you the kind of loss function you want to use and things in that nature. So it gives Monai an idea of what you want to or what you're actually building. The next thing is also important to have a model directory. If you don't create it, I think Monai also creates it for you. But for people that want to do something custom, it helps you to actually have everything more structured and organized in place beforehand. So you need to have a models directory for you to store your model. You have a script that will contain these two important ones, which is your training and your algorithm. You can also have validation, as the case may be. That's why I put the three dots. And then you can also have a test data, which will also have its own metadata JSON and also the actual data set itself.
If you been, do you mind
Yeah,
if we, I don't know if anyone managed to follow everything. So do you mind if we slow down a bit and for us to go through several things again so that we make sure that everyone is on the same page? Do you mind if I ask you several questions regarding what we just went over?
that would be great. Yeah.
So yeah, would you please go back to our main code? Yeah, and we started off just before we code the auto runner, we were discussing the parameters. Yeah, exactly. So yeah, we discussed how to name the different classes, etc. And then we went over to training parameters, which I think is pretty important for the training of the model. Number of images per batch, number of epochs, etc. And how do you decide uh, which parameters will you use? Like if I am to write a code and I need to set up the training parameters, Like, how do I do that? Do I just copy that, or just there is some logic behind it? Like, or what do I need to
Mm,
know to, um, set my parameters in a decent way?
yeah, I think that's a good question. Even me, like my first time using Monai, the actual resource that actually helped me out in answering all this kind of questions, because when I went through their notebook, I was seeing exactly what I was seeing here, but I didn't really have an idea. But then I went into the documentation of Autorunner, and this really explains it in depth how it works, and kind of even give you an example template code of how you might apply it. So these were actually where I actually got the key information of things I really need. So you might see things like HPO, the different arguments you want to use. Let me go into something more. Okay. So things like this, a user can use the one-liner to start the auto trading workflow. So you see something like modality, you see CT telling you that actually it's not only built for MRI, you can actually use it for CT. Um, you can specify different class name. It also tells you that you can also save input dictionary as a YAML file, Um, you can specify a subset of the algorithms to use, and then it shows you how to specify those kind of algorithms, which is exactly what we already use in our code. Then you can specify a local folder with algorithm template to run autorunner, which is also something we've also done. Then you can also specify different training parameters. But the training parameters, it doesn't really explain it to you. It just expects you to already know what each of them does. So, but if I'm kind of someone getting new into this field, I mean, there are a lot of resources out there. I would just want to know what number of epochs per validation means, or what number of images per batch means, or what number of epochs means. And depending on my understanding of it and the use case of what kind of model I want to bring, then I'll know if it's applicable. If it's not applicable, I just really don't need it. So it's also good that we don't just call things and use, we have an understanding of what they can actually help or what they can actually add to the model we are building. Yeah, but this kind of documentation makes it a whole lot easier. And in addition to it, once you've gone through the autorunner, going through the hello world now makes it a whole lot easier because they've now brought those kind of stuff, and within it, they're explaining different concepts of what's happening in there. So something like the data list, in their own case, they just paste the data list for us. But we now understand the data list is important, and we understand that the format they use in creating a data list, and we then created a structure to organize our data set in like format. Um, Generating image and labels, which is also something they actually showed. That is also good that you have something that inspects your simulated or your data set to know that it's actually working. So same stuff, same format, but on your own particular data set for validation. Then the different kind of stuff, but within here, they'll start explaining to you on a very much detailed format what each part does. You understand? So I think they have a whole lot of resources to really help somebody push through. But on our own case, we really want to like bring everyone up to speed, give them something more like a template code containing all the key informations that they might want to use. And it then gives you a ground to then remove things that you don't really need or modify things as the case may be. Nicola, I don't know if that really answers the question.
Yeah, yeah, it answered my question. So from what I understood, just as a recap, um, like what we are providing is just to our audience is just like the bare minimum of creating an AI model for image segmentation. And in order to actually understand what you should add or how to adjust your parameters, or in order for you to know some, or in order for you to get acquainted with some additional strategies, to get your code to the next level, because if everyone's using the bare minimum, it won't be useful at all. You got to go through, for the example you gave, going through Monai documentation and tutorials, and going through that, reading the documentation carefully, and also having a basic understanding of Python, can actually help combining those two things. And what the basis that we are providing are the three main pillars of you being able to create a code for image segmentation model. Is
Yeah,
that correct?
that's very correct. Just as an addition, just because of time, I don't think we'll have the opportunity for people that were thinking of creating like something more custom. We actually wrote like a code, but this code is heavily built on Monai. So it uses all the Monai libraries. But unfortunately, I don't have the time to go through most of the slides. But it helps in things like helping you to build the pipeline for pre-processing your data set to actually building the model. So just for example, things like helping you to load your image. If your image doesn't have a channel, you just have a simple line of command to call, which is your load image, and it then helps attach a channel to it. If you want things like resampling your data set so that it has 1 millimeter voxel spacing, so that irrespective of which machine was using during the scanning, your model doesn't get bogged down in the different units of measurement. It scales everything to 1 millimeter. Things like normalizing your voxel intensity, things like cropping, data augmentation. Mona has already have all this pre-computed, and it's just for you to call that function and then use. I know right here is just having a pseudo code showing us how this pipeline works, but we also have kind of a code that we've already prepared for people to just run. What this code will help you to do is it will help you create the directories and then the files in them, and just gives you some basic kind of templates that you can now improve upon, which makes it a whole lot easier for anybody to want to use. Things like you writing your custom loss function, we already have a folder that will handle that for you. You just need to edit it. Building your own algorithm from scratch, you already have a folder for your algo, and you just need to work on it and edit it. And just as a test case, we also make sure that everything is working on our own test data set. So it's something that is validated and actually work. I would have loved to go through in depth, just giving people an understanding of how it works, but because you can't really cover every single thing in one video, I'm at least giving a high level overview of what's actually there and how easy it is for anyone that is willing to participate, how it's easy for them to get themselves involved.
Yeah, I
I know
totally
friends
agree
here on
with
my
you.
side with them.
Yeah, I totally agree with you that this is great. We're just providing a code, we are explaining it, with the caveat that this is just the bare minimum, and that you gotta also read it carefully and read the model documentation carefully, and also have some basic understanding of Python to create a model of your own. And with all the resources that we're providing and the guidance, it makes it much easier for, I guess, the audience, and for me it's much easier for me to it's still hard, but at least I have some blueprint of how to start, and at least I have some direction of where should I go. It's gonna be a hard way, but I think what you presented was just amazing.
Yeah, and I think if I didn't mention it, if I didn't have the opportunity to mention it, the BRATS community has been really incredibly helpful. So in case anybody feeling isolated or feeling lost or having any issue at all with maybe any of the resources that we're going to provide, is as like we are like I believe that we are actually even very inviting, looking for more people to get involved in what we do. So feel free to actually drop questions via email, which you already have. Just drop your questions via email or any kind of stuff or issues you might be facing regarding what we've already provided or regarding the competition in general, something that we'll be happy to actually help with. But I believe that the resources that we have now, currently the workshop, the IPython notebook we have, and the current last script, which is going to help you create this folder and directory. It's kind of the best you could ever have. And it was actually bettered out of me not being able to customize Monai and build a custom algorithm. I tried it towards yesterday night and today, and it wasn't working. So what I just had to do was to make use of all the libraries Monai offer, and then my knowledge of how to build normal machine learning pipeline to apply them and make it very, very easy, and the bare minimum for people to then add and dissect and add their own logic into.
Yeah, just before people start to log off the meeting, I want to ask one additional question regarding the code and the model that you built. But before that, I'll ask the audience if all of you have registered for the meeting, because we'll be sending out um, several resources. We will send the code that we just presented. We will send some links to libraries and documentation. We will also send a link to the event that we moderated yesterday. It was part of the Rise Mikai Journal Club, where we discussed the BRAT challenge, the educational chapter. We also discussed how to submit to Synapse, which is the platform used for the BRAT challenge. So yeah, all these resources are going to be sent over email. So if you haven't because we have the emails of all the people who have registered for the meeting, and you get these resources. But if you haven't registered, we won't have your email. So please type it in the chat so that we don't miss sending out resources to anybody who is interested. And Vivian, one last question. Where do I rerun the code? Where do I find um, the model that I am about to submit to Synapse? Like where should I be looking for this file?
Yeah, so depending on the algorithm template that you send, the Monai autorunner is going to create a folder that is going to store all the configuration used in creating the algorithm. And within it, you see this model directory. The model directory contains the raw file, two raw files actually. One is a model.pt, and the second one is a model final.pt. So the model.pt is kind of the best model we've encountered since the training, while the model final is the actual the model of the last step of your training. So ideally, this is actually where you get your algorithm. You get it in your model.pt, and you actually want to be submitting your model.pt because it's actually the best instead of your final. For the use case that we have already here, we will, if you actually decide to go through that route, building your custom one, it's going to automatically create it within the model directory for you. We might create something like this, but it depends. It doesn't really matter. It's going to create it within the model directory for you to use. I hope you answered the question.
Yeah, it answered my question. I have one last question. You said about these data layouts. How do you create a data layout of your own? How do you set it up yourself?
Yeah, I think first thing first is, let me be very sure. You're talking about this, right? This list, you mean?
No, no, no. Yeah, just I'm referring to the PowerPoint presentation, the slide you're on right now. Yeah.
Okay. Yeah. One way is to go through the normal route of creating different directory, and within the directory creating the file, but everything is already encapsulated inside this particular cell. So once you run it, it's going to automatically create it for you. The only thing you might want to just change is what you want to call your folder, and then the rest it creates it for you automatically. So to answer the question, you can actually create it manually, but on the other hand, you just run that single script and it creates it for you automatically.
Okay. Okay. Great. Great. Thank you.
And it also imputes, I think it also imputes kind of some basic basic instruction in like a YAML file imputes kind of some basic templates that you can actually modify in the algo, some basic algorithms, training, basic structure for training your data set for you to then now look at how it is and then improve. So I think it's making it more easy for both for anybody coming in as a new person and anybody being an expert. The whole process will be a lot more easier if everything is just set for you to just actually build the algorithm.
Okay, amazing. Thank you. Um, are there any questions from the audience? Like if something's not clear, as Fabian said, you can reach out to us over email, like the email via which you received the invitation for this workshop after you registered. You can just answer or just send a separate message to this email address where you can find us for further assistance or guidance or questions. As I said, you over email, you will receive additional resources and the code that we just presented. Uh, thank you, Fabian, for being a guest to our workshop series. Maybe, eh, as mentioned before, there is so much to cover, and one event is not enough. Uh,
Yeah,
hopefully, we'll meet again. So for a subsequent uh, episode of this workshop series.
yeah, and I want to say a very big thank you for those of us that have waited till till now. So yeah, I want to say a very big thank you to you guys. At least it's kind of a support to the BRATS community and what we're actually doing. And feel free to reach out. To be happy to help, happy to have you integrated in what we do, and try to build it out for everybody so that everybody can get involved in what's like the future, AI and medical imaging. Yeah,
Yeah, yeah. And whoever wants to, because we are thinking of participating in the brush challenge with a model. So if you have some additional knowledge or you would like to contribute in a way, feel free to again text us, because like this workshop event was meant exactly for this, small amount of people, but cohesive amount of people who are enthusiastic about building models and with the perspective of working with us. So yeah, feel free to reach out to us and look for our follow-up email. Thank you again for all of you joining. Uh,
thank you.
we, yeah, bye everybody.
Take care, everybody. Bye. Thank you, Nikolai.